For decades, the search for alien life meant scanning the sky for faint radio beacons, until an object called 3I-Atlas appeared, slowing down as it raced towards our solar system. Official records say its brightening should be simple physics, but across just 4 weeks, its light surged 5 times more than expected. Meanwhile, spectrographs reveal metal traces usually forged, not found, and, against all known comet behavior, this object barely veers off course despite streaming visible gas. If 3I-Atlas is natural, we can explain none of this. If it isn't, we may have just witnessed our first interstellar visitor under intelligent control. So what is hiding behind these impossible signals? Radio telescopes have spent generations sweeping the sky for a single artificial pulse, a beacon, a whisper, some coded invitation from another world. But in the silence, another channel has opened. Every so often, a solid body crosses the gulf between stars and enters our solar system. A macroscopic technosignature, if any exist, would look like this: not a signal, but an object. Since the dawn of modern astronomy, only 3 such visitors have ever been confirmed. The odds are staggering. For every 100 billion comets that circle the Sun, only 1 or 2 have come from another star. Each arrival is a cosmic lottery ticket, a chance to catch something built, not born. Traditional SETE, with its focus on radio and laser signals, assumes that civilizations broadcast. But what if the best evidence is physical, silent, inert, drifting through space? Objects can preserve information, technology, even intent, long after their makers are gone. Unlike a fleeting transmission, a macroscopic artifact endures. It can be studied, measured, and, if the timing is right, intercepted. The scarcity of these interstellar objects makes every detection a global event. Oumuamua in 2017, Borisov in 2019, now 3I-Atlas. Each one is a singular opportunity, a probe from a time and place we may never see again. Their rarity means that even a single anomaly carries weight. The universe offers few second chances. SETY's original vision was shaped by the tools of its era: radio dishes, signal processing, a search for patterns in the noise. But the discovery of Oumuamua rewrote the playbook. Suddenly, the search for technosignatures included not just what we hear, but what passes by. 3I-Atlas is not just another comet. It is evidence in transit, a messenger from another system, and perhaps, if we're prepared to look closely enough, a sign that we are not alone. On May 7, 2025, the Transiting Exoplanet Survey satellite, TESS, recorded a faint, fast-moving object against the thick star fields near the galactic center. At the time, no alert went out. The signal was buried in a digital sea of stellar clutter, its motion too subtle for automated triggers, its glow lost among thousands of background stars. For nearly a month, the object swept onward, captured night after night in TESS full-frame images, each exposure stacking another faint trace onto archival hard drives. It wasn't until July 1st that the Atlas survey, scanning from its Chilean node at Rio Hurtado, flagged an anomaly. The object had brightened sharply, 5-fold since TESS first caught it, yet its position still hugged the crowded bulge of the Milky Way, a region notorious for hiding transients in plain sight. The Minor Planet Center logged the alert, and within 24 hours, the world's observatories pivoted to follow up. In the days that followed, teams combed through old data. Zwicky Transient Facility and Pan-STARRS both turned up pre-discovery images from late June, their own records showing the object's trail as it moved steadily across the sky. Amateurs joined the hunt, sifting through public archives, their finds filling in gaps from June 14th through the end of the month. Each new point on the timeline added detail to the light curve, revealing a surge in brightness that outpaced any simple geometric explanation. The culprit was the sky itself. The object's approach from the direction of Sagittarius meant that even the most sensitive surveys struggled to separate its signal from the background. Only after the July announcement did the full scope of its early activity become clear, thanks to a forensic sweep through terabytes of archival data. For the TESS and Atlas teams, the discovery was less a single spark than a slow burn, lit weeks before anyone realized an interstellar visitor had arrived. Between May 7th and June 3rd, 3I-Atlas brightened by a factor of 5, an increase that defies the usual playbook for distant comets. Standard geometry predicts only a modest rise, maybe 1.5 times brighter as the object shifts from 6.36 to 5.46 astronomical units from the Sun. Instead, photometry from TESS, ZTF, and ATLAS shows a surge, fivefold, steady, and persistent across nearly 0.9 astronomical units of travel. Each survey's numbers line up, cross-checked against field stars and synthetic solar analogs, with systematics below 1/10 of a magnitude. This isn't a brief outburst or a fluke of instrumentation. The light curve, reconstructed from nightly stacks and shift-tracked exposures, draws a clear arc, rising smoothly even as the object threads through the crowded galactic bulge. At 6.36 astronomical units, activity is not expected. Water ice stays frozen, the Sun's warmth is a distant memory. Yet the coma is already visible, and dust cross-section measurements jump from about 300 square kilometers in May to over 1,700 by July. The numbers hold up under scrutiny, with error bars tight enough to rule out random scatter or background confusion as the cause. Stacking up the flux, the odds tilt sharply away from geometry alone. The excess light demands an explanation, one that fits both the timing and the scale. No single survey, no matter how deep, can account for the magnitude of the change. The data, laid bare, leave little room for ambiguity. 3I-Atlas was already active, and already an outlier, before it ever made the official record. The search for answers begins with the numbers. A fivefold jump in brightness, outpacing every geometric prediction, demands more than a passing glance at the data. Astronomers run through the usual suspects: instrumental error, background confusion, a lucky line of sight through the galactic bulge. Each is tested, cross-checked, and ultimately found wanting. The light curve holds steady across telescopes and continents, its arc too smooth for a fluke and too early for classic cometary activity. Some suggest the object's true closing speed might have been underestimated, masked by the dense stellar fields of Sagittarius. But even after correcting for crowding and recalibrating the photometry, the excess flux remains. The numbers simply don't add up to a natural slow burn. That leaves the door open to bolder ideas. Could 3I-Atlas have fired thrusters, an engineered braking maneuver to match solar system velocities? It's a hypothesis that lives on the fringe, but the timing fits the data. A controlled deceleration, executed far from the Sun, would explain the early, persistent brightening without relying on water ice or familiar volatiles. If so, the object's activity would be the signature of intent, not accident. Yet, for every speculative leap, a counterweight of caution. The sky is notorious for tricking even the most careful observers, and the burden of proof is heavy. As the debate turns, attention shifts to the chemistry of the coma, where the next clue may be hiding in plain sight. VLT spectrographs, tuned to the faintest whispers of atomic light, picked up a puzzle in the coma of 3I-Atlas. Nickel lines, clean and well resolved, rose above the background, yet iron, which should have been there in lockstep, was nowhere to be found. The team at Paranal spent nights double-checking calibrations, rerunning telluric corrections, and cross-referencing laboratory wavelengths. The answer held: nickel was present, iron was not. No comet in the solar system has ever shown a ratio like this. In most, iron and nickel travel together, locked in a partnership forged in supernova and planetesimal cores. The Sun's own photosphere holds about 18 atoms of iron for every one of nickel. Even among the dustiest, most metal-rich comets, nickel rarely outpaces iron by more than a factor of 2. Here, the ratio blows past 15, perhaps 50, with iron lines buried below the detection floor. The VLT group, led by Dr. Sofia Cardenas, mapped the Ni transitions in both moderate and high-resolution runs. Production rates hovered around 4.6 grams of nickel per second at 2.85 astronomical units, with robust upper limits on iron that forced the Ni/Fe ratio off the charts. Every attempt to tease out a hidden Fe signal, stacking exposures, probing for faint blends, came up empty. Natural mechanisms struggle to explain it. Thermal decomposition of nickel carbonyl, a fragile molecule that vaporizes at low temperatures, could boost nickel release, but iron carbonyl is less likely to form or survive. Some theorists point to selective sputtering or exotic fractionation during planetesimal birth. Others, more boldly, raise the question of engineered residue, nickel-rich superalloys eroded by ancient engines, leaving their mark in the coma. So far, the spectrum offers no propellant lines, no obvious signature of fuel or alloy. Only nickel, standing alone, and the silence of iron. The elemental ledger is unbalanced, and the search for a natural explanation continues. Measured by any standard, the trajectory of 3I/Atlas is a paradox. Astrometric fits from July through August show a drift of just 1 to 1.5 kilometers per day, barely a nudge, even as the coma and tail stretch for hundreds of thousands of kilometers behind. For comets in the solar system, outgassing acts like a rocket. Jets of vapor push the nucleus off course, producing a measurable non-gravitational acceleration. But here, the numbers barely budge. The path is almost gravitationally pure, as if the object were inert stone, not an active comet venting gas and dust. Stacking up the data, the suppression of this rocket effect stands out. Borisov, the last interstellar visitor with a strong coma, drifted by about 100 kilometers per day, nearly 2 orders of magnitude higher. Even a modest tail should nudge the nucleus, but 3I/Atlas resists. The anti-tail, the dust, the visible jets all appear in the images, yet the orbit remains stubbornly unaltered. Models that account for the observed mass loss and surface area predict a much larger trajectory shift. The numbers refuse to cooperate. If the object were a mountain of ice and rock, the only way to dampen this effect so completely would be sheer mass, something so dense and enormous that even the strongest jets would barely move it. But photometry and surface brightness profiles put strict limits on the nucleus size. It is large, but not implausibly so. The alternative is control, active stabilization, constant correction, or a shell that absorbs or redirects the thrust. No known natural mechanism can fully explain the gap between what we see and what we measure. Each astrometric update tightens the error bars. The drift stays locked at just above a kilometer per day, far below the threshold where comet physics would expect. The numbers are clear. 3I/Atlas is moving through the solar system as if it were immune to its own activity. The contradiction is mechanical, not just mathematical. In the realm of natural objects, motion follows mass and force. Here, the rules bend, and the path barely wavers. On the scale of interstellar visitors, Borisov stands as the textbook case. Its coma and tail, rich with cyanogen and diatomic carbon, traced a classic arc through the inner solar system. The numbers matched expectations. Non-gravitational acceleration clocked in at about 10 to the -6 astronomical units per day, translating to a drift of nearly 100 kilometers daily. Every jet of vapor nudged the nucleus, every outburst showed up in the orbit. Borisov behaved like a comet should, obeying the physics of mass loss and solar heating. Oumuamua, by contrast, played by no familiar rules. No visible outgassing, no dust, no coma. Yet its path veered sharply near perihelion, with a non-gravitational acceleration on the order of 2.5 times 10 to the -4 astronomical units per day. That's 37,000 kilometers of drift, all without a single jet or tail to blame. Its rotation, a steady 3 turns per day, only deepened the puzzle. Models ran aground. Too little mass for a snowball, too much movement for a rock. Now, 3I/Atlas enters the ledger, but in the opposite direction. The coma is undeniable. The tail stretches for hundreds of thousands of kilometers, and yet the measured drift barely registers, just 1 to 1.5 kilometers per day. That's 100 times less than Borisov, a fraction of a percent of Oumuamua's. The rocket effect is missing where it should dominate, present where it should be invisible. 3 objects, 3 patterns, none fitting the same mold. The universe, it seems, deals its wildcards in pairs of opposites. Rubin Observatory stands ready on Keropachon, its 8.4-meter mirror poised to sweep the southern sky every few nights. With the Legacy Survey of Space and Time, LSST, Rubin brings a new era of early warning. Its cadence and sensitivity mean that the next interstellar visitor, whether comet or something stranger, won't slip by unnoticed in a crowded starfield. Alerts will go out in real time, giving professionals and amateurs alike a running start. But telescopes alone can't catch every twist. The last two interstellar objects proved that. When 3I-Atlas brightened fivefold against the galactic bulge, it was amateur astronomers who trawled through terabytes of archival data, stitching together the first clear light curve. A network of citizen scientists, armed with backyard setups and open-source software, filled in the gaps between survey passes. Their rapid reporting turned scattered images into a timeline, catching activity that would have vanished into noise. Now, the stakes are higher. As Atlas rounds the sun, every night counts. Coordinated campaigns, Rubin's nightly sweeps, Pan-STARRS in Hawaii, Atlas in Chile, and amateur stations from Pretoria to Perth combine into a global net. Each observer adds a data point, shrinking the error bars, sharpening the models. The next outburst, the next spectral anomaly, could come at any hour. Early warnings ripple through Discord servers and Telegram groups, triggering impromptu follow-ups from telescopes large and small. The call is simple: eyes on the sky. Track the light curve, chase the spectrum, share the raw frames and the calibrated stacks. In this new SETI, discovery isn't reserved for professionals. Every alert, every image, every measurement is a step closer to catching the improbable. A message written not in radio, but in motion, chemistry, and light. Spectroscopic observations from the Very Large Telescope show nickel in the coma but no iron, an unusual signature, while astrometric fits reveal almost no non-gravitational acceleration, even as visible outgassing is present. In contrast, 2I/Borisov displayed typical cometary drift, and 1I/Oumuamua showed significant trajectory change without any detectable outgassing. These opposing anomalies remain unexplained by current models. No evidence confirms artificial control, but the physical contradictions in Atlas's behavior challenge accepted theories. Our best clues may arrive not as signals, but as objects whose very motion defies expectations.